Okay. At the moment, I'm interacting with Blender version 3.622. The newest version is 4.2. The layout is the same. The commands are the same. There is a certain add-on that works better for this version, and it's easier to demonstrate for the course of for this kind of hands-on session. Okay, so what do we see in the main window when we open Blender? We see basically a cube, which is the standard kind of object. We have a camera, and we have a light. And essentially, those are the ingredients for rendering an image, or even just seeing with your eyes, right? So basically, to be able to visualize our target scene, we need to somehow get these objects as subjects into our scene. So before carrying on with the Blender GUI, let's just try to prepare these molecules, or like these subjects, these complex structures. And that is the reason why I was sharing the notebook. So basically, again, I'm assuming that a lot of you have interacted with Python before. And I think it's safe to assume. So essentially, like on the Git repo that I shared the QR code before, there is just a readme.md. That is the only main file, and that is just a cheat sheet of some of the functions that I use. So if you want to play around with this kind of like a molecular representation that you can reproduce quite easily. But in principle, basically, to generate our subjects, we can say, well, basically, this notebook will run in virtually every environment because it just needs ASC and RDKit to run. In addition to this, there is a package called AutoAbsorbate, here imported as AU as a link to Gold, Colorado. And basically, like this AutoAbsorbate package has a couple of helper functions that are quite convenient for what we want to do here. So, for example, we have one of the intermediates, phenyl bromide, for example, and we can represent it as a smiles here, and just convert it into a ASC atoms objects. Which looks like this. We can use this atoms object to write it to a trajectory later. Okay, we have more than just one molecule in the scheme. So let's take all 4 actual molecules and use basically AutoAbsorbate fragment object to initialize those. Okay, that's already done. Now we turned our attention to the metal complex. Now, metal complexes are a little bit more complicated than molecules because the classical force field driving the RDKit initialization doesn't deal with complex geometries. But the nice thing about if we're just drawing a scheme is that we don't have to be very pedantic about what is the exact structure of the complex, but we are satisfied with something that looks like the correct thing. And if you want to confirm it, we could actually run some quantum chemistry on top of that. So here we have a helper function. Basically, we provide a central atom, which is the metal atom in the center. As a ASC atoms object, we provide the smiles. So basically, we have a tetrahedral, for example, tetrahedral ligand. We provide 2 ligands as smiles, and we provide the substrate as smiles. And we provide the vectors that are kind of, if my head is the central metal atom, tetrahedron 1, 2, 3, 4. And basically, we have this function. Now, the only thing that we need to initialize, let's say, a ligand that is facing, kind of orientated in such a direction corresponding to the geometry of the complex, we need to provide some kind of this information of the directionality of the bond in some way. We can do this with a concept called surrogate smiles. So, for example, this would be a 3-methylphosphine ligand, and we were just putting a kind of a surrogate atom, in this case chlorine, that binds to the phosphorus. We fully intend to delete the chlorine atom in the next step, but we remember its relative position to phosphine. And if you remember the relative position, then you can just rotate this vector in any way that you see fit. For example, to align it with the vector corresponding to the central metal geometry. Okay, complex geometry can be linear tetrahedron for our case. So basically, we can call this function that we just described to generate the linear complex and to generate the basically the ligand substrate complexes. The reason why I chose to show you this example is because like the same principle, and particularly in the auto-adsorbate package, you would find kind of convenient, easy ways to interact with surfaces, clusters, complexes, like using this kind of simple descriptors of surrogate smiles and vectors on the surface or on the cluster or on the complex or whatever. So it's quite useful for initializing initial structures for any kind of simulation. And it's also useful for this kind of example drawing. Okay, we collect the trajectories. And let's say one of the important things is that, okay, I'm coming from my perspective, I'm a little bit lazy, so I don't like to click around in GUIs. And Blender is really made for clicking around in GUIs. And the problem is that if you just take all of these atoms objects that we just constructed and put it in a trajectory, which is this collected traj, and if you write them, and so here I'm printing just the formulas of each individual molecules. You can see that they have different formulas. Now, if you take basically this collected XYZ, collected traj XYZ, which has 6 frames or something like that, and you take that and import it in Blender, this will give you some weird looking structures because Blender was made for visual, well, the add-on for importing XYZ files was made for molecular dynamics. So that means each frame has the same number of atoms and all of the atoms are sorted in a certain way from frame to frame to frame to frame to frame. If you disturb this, it will just remember what was in the first frame and kind of like make atomic swaps in these trajectories. So there is a utility function in auto-adsorbate that's called getBlenderized, and that will just kind of add the non-existing atoms in certain molecules somewhere to the side so they don't disturb. Okay, cool. We have our blend traj, so we have our subject now. Okay, back to the Blender GUI. So I will switch on just one thing so that you can see. Do you see this white thing here? This is basically an indicator of what I'm pressing and clicking on my keyboard. So basically, like the idea was to record the session and share it later. So if somebody actually wants to do something like this and cannot remember what was the exact procedure, so they can look it up. So basically, we have a subject. So this is where our structures go. We have a light. We have a camera. We need to be able to orientate somehow in the scene. For this, depending if you're using Mac or Windows, it could be different. But essentially, you have this circle here. So if you click and hold on this circle, you can move your screen around. It always rotates around kind of the set point of the scene. You can also grab hold of this kind of hand and move around in the scene. You can zoom again in the same way, or you can click and look to see what the camera sees. So if you press here, you see what the camera sees. Unpress here. So basically, this view is just a view of you walking around the scene, setting stuff up. This view is the view that you will render once you press the render button. Okay, I'll press the N key to open this menu here and go to item. So we have in this part of the scene, in this part of the screen, we have the camera selected. So basically, the camera has a bunch of properties. Most importantly, location and rotation. And we also have some additional properties if we click here in this lower screen. So for example, I don't know if somebody is like into photography, you can change focal length, aperture, and these kind of things. At this point, we can just change the location and orientation of the camera. So let's put it at, I remember exactly what it's supposed to be. Let's put it at -1, -22, 0. And then let's put the rotation to 90, 0, 0. Perfect. Okay, so now we have some kind of a side view of the same box. And it's relatively easy to move the camera around. You can do it also from different views. For example, like if you click the Z axis here, this will take you to the top view. And now you can see, oops. So basically now you can see the camera here. If you select any object, camera or cube or whatever, you can basically click on the camera and press G once, and then you can move it around. So, or you can, for example, let's go to the side view and say press R to rotate, and you can rotate the angle of the camera. So if you point the camera, I don't know, above, below the object and take a look, what does the camera see? It misses the object completely. Okay. I will put this back to 90. Okay. We want to make a render of cubes, so we will remove the cube. To remove a cube or any object for that matter, you can press X or delete, and it will give you this prompt if it's okay to delete or not. At the moment, we can also delete the light because we will add a different one later. Okay. If you're starting Blender 3.622 for the first time, you will be able to, well, you will have to go to Edit, References, and then look here for Atomic Blender. I already switched it on previously. So basically, this is an add-on, which is essentially a Python script for importing PDB and XYZ files. We saved XYZ, so we will be importing XYZ files. So basically, if you're using 3.6 and this is not clicked, you can click it, and then you will get the following. And the following is File, Import, XYZ. This gives you another window that you can use to navigate to your data. So we have we have the collected trudge and the blend trudge. So you remember the collected trudge, I said there was some problem with Blender rendering the atoms, well, importing the atoms as this kind of instances of spheres and all of the geometry that Blender has to add. So I will try to add the collected trudge to exemplify what I meant by this. So basically, in this case, so there is a routine that will try to center what you're trying to import in the scene. I already know when I was generating the molecules that they are centered in a way that is good. So you can unclick this object to origin, and you can say load all frames and press import. Okay, so this looks weird, right? Which is exactly what we would expect to see because we are aware of the problem. So now most of the interaction with the GUI was happening in this main window so far. And I was mentioning this kind of part here in which you can select different objects, and this part here in which you can kind of access settings of different objects. There is also now kind of another point comes into focus, which is this timeline window. So here you can see that each of these yellow dots represent a frame of the XYZ file that we generate. And if you scroll through those, you'll see that actually all of them are wrong except the first one, which is exactly what we expect. So I will just undo the import, and then let's try with the proper trajectory. So here we have the complex, or this would be kind of like the pre-transmetallation complex. This would be the oxidative addition pre-complex or post-complex, the ligand itself, one molecule, so magnesium bromide, methyl magnesium bromide, phenyl bromide, and so on. And so basically, the cool thing is that now we can go to our camera view. And if we scroll through, we have essentially all of the molecules in frame, almost ready for putting shiny stuff on it. Okay, first thing that we can notice is that, okay, this is not the most flattering representation of phenyl bromide. it is, let's say the angle is weird. So to adjust this, it's not super difficult. Okay, in the scene collection, here you can see we have the camera, which is selected at the moment. And we have this additional collection, which is called blend_traj.xyz, which is essentially all of the information contained in the XYZ file. If we want to collectively adjust all of the frames of this trajectory, we have to right-click it and say, select objects. Now, all of the rules that we were using to kind of rotate, move the camera around apply. So basically, we can say G to move stuff around, escape to skip it, or we can say R to rotate. And we can say, for example, if you want to rotate around a certain axis, you can say RX to rotate around R axis. And as you can see, it is rotating around the X axis, which is kind of parallel to the screen, but it has a very long lever. The reason for this is that we were doing this kind of get blenderized trajectory, which takes all of the extra atoms and puts it somewhere. So Blender is rotating around the center of mass of this object, and we have something that we are hiding kind of under the carpet. So we have to rotate around something else. For this, we can basically like go into this drop-down menu here, so basically transform pivot point is usually at bounding box center, but you can also put it to the 3D cursor. The 3D cursor is this kind of cross here. And now if you say Rx, you can rotate the molecule as you wish. So I was playing around with this earlier, so I think that this should look kind of okay for all molecules, but we can check. Okay, so the ligand is a little bit weird. This is also not great. This is also not great. We don't see the bromide. We don't see the phenyl. So let's try to optimize the rotation of this molecule first, and then see how do the other molecules look like. So let's try to rotate around X a bit more. For example, something maybe like this. Okay, this is not good for the complex. Let's rotate a bit more. This is also not good. Let's try to rotate around set. Maybe we can find something like this.
Why do we do it not independent of the other parts of the frames? Because it's like different molecules, right? Like, why do I have to rotate them all in the same way? Can't I just rotate one and it looks good, then I rotate the next one independent of the first one?
Yes, it would be possible if you didn't import it as a trajectory. At the moment, it still thinks it's an empty trajectory, therefore all of the frames are connected. Now, this is another mode of operation that comes with additional kind of like a bit of a headache. So basically, like if all of your atoms are contained in a trajectory, you can edit the materials and the sphere size and all of these things together, like in one place. If you have different XYZ files and different collections for each of the molecules, we have to edit these separately, or at least set the materials of each individual atom separately.
There's no possibility if I have them already in one collection to still manipulate one of the objects independently.
Not that I know, at least not using this add-on. But in principle, it should always be, it should always be possible to get something at least reasonably good. And I mean, if you're really struggling, then I would definitely advise to go for kind of the fallback options that is importing individually the structures. Okay. Let's call this pretty good. Okay, so again, we are, let's say that we are happy with the orientation of the molecule and the camera and all of the species. So basically, now we are looking at the scene from the camera view. And you can see that, first of all, the camera has a little bit of distortion going on. If we select the camera here, and basically go into the camera settings, we can see that there is a focal length that we can set to the camera. shorter focal length, for example, if you put something really short, like 18, will give you a very wide field of view. If you come closer to compensate for this wide field of view, for example, you move the camera to minus, I don't know, maybe it's too much, to minus 10. You can see that basically, because the camera is wide, or the lens is wide, it is distorting the shape of the molecule, meaning that things that are further away from the center of the lens look inflated or big. So usually it is a matter of taste, but what I tend to find to look the best is quite long lensed views. So we select something that is around 100 to 150. Usually that looks really good for molecules. And we need to move the camera backwards. Since this is just typing in a number and it doesn't require any walking, it's quite easy to do. And basically, now we have, let's say, a more reasonable lens for what we want to do. We can select the camera, press G to center a little bit the camera with respect to the subject. Okay, maybe a little lower. Okay, all subjects are in frame, but this is kind of a 1080p or like a widescreen format of the proverbial sensor, which we can also adjust. Here you have a couple of settings tabs, and in this output tab, you can find the resolution in X and Y. Since I'm running an 8-year-old laptop without a GPU, I will put just 500 in this case. And since, okay, this changed a little bit the look of the scene, so I will change the camera setting, well, basically the camera focal length to compensate. So basically I'll put this to 150 to zoom in additionally. And maybe we can check if still everything fits. Yeah, seems that it looks good. Okay, so we set up the camera, we set up the subject. What is missing? The lights. So at this point, we need to kind of like, we have to address the missing ingredient, which is light. And to talk about light, we need to talk about the render engine. Blender has 3 preset render engines. Eevee, which is kind of rasterized engine that is usually what you see in kind of older games, meaning that light is not physical light, it's kind of pre-baked light. There are some kind of set of rules, parametric rules to get stuff to interact with light. There is Workbench, which is, I think it's called a potato now, and Cycles, which is a proper ray trace engine. So basically, I tend to use Cycles. It is quite slow, and paradoxically, like for the render of this nanoparticle under molecular dynamics, the render took substantially longer than the dynamics itself. So yeah, but as long as you're making smaller things for one figure, I think it's fine. The CO2 footprint will not be too bad of your work. Okay, so we choose Cycles in this case. We set the rendering engine. Our scene didn't change at all. That is because, again, in this 3D view window, there are multiple modes of observing things. And what we are looking at now is, I forgot actually, what is it called? Viewport shading. So this is something that helps you locate your subject, object, camera, and lights. We can switch to rendered view, which will be, which can be done by, if you press Z, you get this 4 options. And if you click rendered view, you can see how will the scene look like through the lens of the actual render engine. And as you can see, this looks pretty bad. First thing is the background is gray. And if you want to make kind of like a figure that is supposed to be printed on paper in a PDF, we want something that will play well with gray. And actually, if you could avoid having a background altogether, would be nice. So we can do this. We can set the let's say the world color to alpha equals 1, so full transparency. And we do this in one of the settings here. So here, so basically under render film, for some reason, there is a setting called transparent. So if you set this, you get a transparent backdrop, but still the molecule looks at least weird, actually unacceptable for any kind of scheme. So, but we are missing the light. So we can add anything to the scene, including the light, by pressing Shift A. You can say add light. You can choose the area light. And now we can position our light. So G, I would put set lifted somewhere on top. Maybe go to the top view. So press here on the top view. Say scale by 10. Maybe a little bit more. Usually a bigger light means softer shadows, and softer shadows work nicer with kind of printed media. So let's call that kind of good enough. And let's see what the camera sees now. Almost nothing. The problem? Well, basically we added a light. We added the area light here, but the intensity of the light is very low. So if we select the light and go again into this property menu, we can find the intensity of the light in watts here. So if we elevate it by 100 times, it's still not enough. Still not enough. Okay, something is starting to happen. Okay, so we have some light. It is coming from the top though. And usually, again, if you want to have kind of interesting looking shadows, it's good to have more than one light. So basically, if you can see, here we have kind of like a hot spot, like a bright spot on the top of the sphere here. And we have some shadowing happening here with the interfaces of the spheres. To make that again look even better, or like at least good, we can just add additional lights if we can find them. The reason why we needed so many watts is because the light is very far away. Okay, so I moved the light, I don't know, at 200 meters away in human units away from the subject. So obviously it was looking not great. Okay, so now we're obviously being overexposed. So we can turn down the intensity of this light. 1 megabyte seems to be too much. Okay, this is maybe too less, but we were getting close. So 50 kilowatt looks pretty good. We can look at it from the Y direction and say, okay, this light is here, let's add another one. And we can do that by selecting the light and pressing Shift D, and that is a duplicate command. So basically now you can just move the mouse and you effectively have generated another light here. And let's put this one to face kind of from the direction of the camera. So somewhere from here, and maybe we can rotate it so that it's pointing towards the subject. Press R. It's rotating around the pivot point. So actually what we could do, you just say, after duplicating without moving it, we can just rotate. So Shift D, Escape, R, and place it here. What was the effect of this? It's slightly better. The second light could be a little bit lower, so let's lower it a little bit more. Aha. Do you see the problem? The light is pointing at the opposite side. So it's illuminating the backside of the molecule. And the interesting thing is, like if you have you heard of Fresnel reflections? So that is basically like reflectivity of a surface goes to 1 if the angle goes to 0. So you can see here, since it's a physics-based rendering engine, you can actually see that there is a kind of like a white glow around the subject if you have this kind of backlit situation. And this I found to look quite cool if you're printing on white paper, because it makes kind of the molecule belong on a white background. So actually this was not intentional, but let's leave it on, why not? Okay, so now I will just do Shift D of this light and make another one. And make another one from the front. And let's see how this looks. And here we are. This is not too bad. Like for white paper, I think the kind of exposure is in the ballpark. Let's see how the other molecules look. Also not too bad. So one additional thing that you might want to touch as you are playing around, well, preparing your figure for submission, would be maybe the colors and the individual kind of values of the individual materials. Again, Blender is really good for editing materials. It has a complete kind of material engine in the background. So basically, if you noticed, I was kind of pointing my mouse to the lower left corner. When it becomes like a cross like this, you can press, hold, and drag. And you can divide any window into as many sub-windows as you wish. And once you have kind of access to one of these windows, you can click on the top left corner and you can choose what kind of editor you would like to see. It can be a timeline editor. It can be even another 3D viewport. But here we want to choose a shader editor. And basically, the shader editor allows us to have access to all of the material properties of the individual materials that are kind of decorating the surfaces of the spheres that are representing the atoms. So how do we access the individual properties? So for example, like now we are looking into the collection itself. So basically blend strach.xyz. And here we have, you can see like sub-collections, carbon, hydrogen, bromine, magnesium, palladium, and so on. So basically, if we just focus on carbon for the moment, we can go carbon, carbon atom, carbon mesh. There is a carbon ball. If you click on the carbon ball, you can see that in the shader editor, something happens. And basically, what you see here is kind of a node representation of the logic of that is constructing the surface properties of the individual materials that are kind of giving the color and the reflections of the atoms. So basically, you have two nodes, materials output and the principled BSDF. This principled BSDF is a super nice node because it has all of the properties that you would need to make something look photorealistic. So basically, it's not really important to go into the details, but the one that we do care about is the base color. So if we want to make things look darker, we can basically lower the value to something maybe a little bit more contrasty, like here. Or you can, let's say, okay, my carbon should be green, I don't know. You could edit these things here. For me, I prefer carbon to be gray. And usually most of the chemistry journal scientific editors. Another setting that I like to play around with, so basically there was the base color, and there is another one which is called the roughness. If you set this value to super high, like actually maximum is 1, you can see that you have almost no reflections on the spheres because kind of the surface roughness disperses the light. Or you can make it go in the other extreme and make it super reflective. And then you have kind of perfect billiard balls representation. Usually what looks good from my experience is something around like between 0.3 and 0.5. If you want a bit of a shinier look like I do now, 0.3 is the sweet spot. Okay, so basically we edited this material carbon, changes the base color, and changes the roughness. So let's do this for the rest of the materials as well. So we go again in the scene collection, navigate to hydrogen, navigate to find hydrogen ball. Now we're editing the hydrogen material. The color is fine. Maybe we reduce the roughness to 0.3. 0.3. Bromine. Maybe we can go to a frame that actually has bromine to see what's up. Okay, bromine is a little bit dull, the color. Maybe we can add a little bit of saturation here. So if you add a slight bit of saturation, maybe put down the value to make it a bit more contrasty. Bromine is one of the main kind of reactants in this reaction. And we can put the roughness to 0.3. Magnesium as well. Let's keep the color as is, put the 3. Okay, palladium is a bit different than the rest of the elements here, right? Palladium is actually a metal. Now, depending on your preferences, you might want to keep it in the same representation as the rest of the atoms, or you might want to use another property of this principal shader, which is kind of the metallic slider. So basically, we said base color has its field, we had the roughness has its field, but there is also a slider that is called metallic. So basically, it can be changed continuously from 0 and 1. The only thing that makes sense, in my opinion, is 0, which is dielectric, or 1, which is metallic. So if you put the metallic slider to 1, you can see that we got a disco palladium. The roughness still behaves in the same way. So if you put, I don't know, 0.1, it is a very glossy material. So you can actually see the reflections of the individual ligands on the palladium. You can see the lights. If you put additional stuff in the scene behind the camera, it will reflect there. So you can kind of achieve cool effects. Like if you're making a cover or something, like it's a cool way to represent stuff. Usually, if you're making a very small kind of like graphic that is supposed to be in a a scheme containing a lot of information, I would probably go with something a little bit more conservative, meaning either putting the roughness to a higher level so that you cannot see all of the detail. So 0.6, you can see that it's metallic, but it doesn't have all of the detail. Or you can just leave it as a dielectric. And then maybe put the roughness a little bit lower. Good. So now we got the hang of all of the materials. We got the hang of rotating, moving, importing. The final thing to figure out is the rendering. And you were asking about kind of like, why do we have to move things together? Well, the nice thing about, well, that is a bit of a problem of having all of your frames in one trajectory, but the moment when it pays dividends is the moment when you need to render it. Because if you have your, let's say, frames, your kind of molecules in a trajectory, you can just render all of them at one time as an animation, and just set the output format to be PNG, which is what we can do. So basically, we need to figure out where are the output settings. And here, if you go to render, you can see that there are a bunch of things to touch. The only thing that we care about is this render box here. So it is a ray tracing engine, which means that it's kind of like actually tracing kind of simulated photons and capturing it with the camera, which means that if you collect more photons, you will get a smoother image, nicer image, and so on. In situations like this, in which we have relatively simple materials, relatively simple scene, you don't really need a lot. So, which means that I can render it on my CPU faster than I would be running the molecular dynamics with the SOAP gap. So I will switch off the noise threshold and put only 100 samples here. And Okay, so this is maybe ready for a test render. So let's just render one frame to see how fast it renders and does it even make sense to render the whole thing. So I'll just go to render image, and this will render the current frame. Okay, this was not too bad. 10 seconds per frame, that's not too bad. The quality could be more pixels. On my computer, no need to do that. But if we wanted to increase, let's say, the resolution or the quality of this render, we could either increase the number of samples, that would reduce the noise, or we could go here and put the percentage kind of resolution X is 500 by 500, we could scale it by 2. So like 200 here would be 1000 by 1000. And it will basically quadruple the render time. So I will leave it at 100 for now. Okay, so we are good to go, basically. Now we need to set the destination of our render output. And let's put that in the current folder. Let's put it here. As you can guess, I tried it before. Okay. So basically, we set output destination. We set the file format to PNG, RGBA. So we want to keep the alpha channel so that we have transparent backgrounds. And now we can just go back to, well, we can Control S to save. And then we can go to render and render animation. And basically kind of kill time for 40 seconds while the renders are done. And once the renders are done, we will have all of our files waiting for us in the directory.